Today we're going to talk about solving polynomial equations by factoring. Factoring is an essential skill, something you need to know, and we are going to be relying a lot on information we've already learned for today's lesson. So our guideline steps of factoring really haven't changed. We're still going to set the equation equal to 0. We'll take out a GCF. Taking out a GCF makes your number smaller and your life easier. Sometimes it even makes the polynomial factorable when it wasn't before. Then you're going to factor using strategies we know and some new strategies you'll learn today. And then you set each factor equal to 0 to solve. Our first example, solve each polynomial by factoring. We're going to go ahead and set this equal to 0. I'm going to move everything to the left-hand side, resulting in this polynomial. Now, this polynomial kind of looks like our quadratic equations did. I'm going to utilize my x method to try and factor it like we traditionally do. See if there's anything we can replace that middle term with that'll work out. Now, because I'm not dealing with a quadratic, I'm not going to use my trick. I'm going to multiply the first term times the last term and add to the middle term. The good news is my variables will work out because if I multiply n x squared times n x squared, I get x to the fourth, and I would be able to add my like terms and get that x squared. So that's a good sign that factoring this way is possible. Now I have to think about my numbers. What multiplies to -6 and adds to 1? That would be +3 and -2. These are the two terms I'm going to replace my middle term with here. I'm going to write the remaining of the polynomial. We group the first two terms, take out what they have in common. In this case, it's an x squared. They both have 2 copies of x, leaving me with x squared plus 3 in the parentheses. I'm going to group the second two. These only have a 2 in common, and I'm going to take out a negative because it's a sign of the third term, leaving me with x squared plus 3. I like that because my parentheses match. That means that this is factorable. So we're going to take out x squared plus 3 as one of our factors. And then the outside, the GCFs of the 2 terms become our other set of parentheses. And I've fully factored this polynomial. Now I do want to check. I do see an x squared with a minus sign, so I'm on the lookout for a difference of squares. But 2 is not a perfect square, so I'm not going to be able to apply that formula. My next step is to set each of these equations equal to 0 and solve. Now they're quadratic equations. I like that because I know how to solve quadratic equations. These ones are pretty easy quadratic equations too because I can use my square root method, remembering to account for the plus or minus when I take the square root of both sides, and the I when I take a square root of a negative. I end up with 2 of my roots being plus or minus I square roots of 3. And then on this side, I end up with plus or minus a square root of 2. So my final answer for x, solving by factoring, would be plus or minus I square root of 3 and plus or minus a square root of 2. You want to gather them somewhere, put them together to record your final answer clearly, because sometimes our work can get kind of messy. So this is a strategy we know, and it works with some higher order polynomials or polynomials of higher degrees. A new method for us is factoring by grouping. This method is used when you're working with a polynomial that has an even number of terms. You can try this method anytime your polynomial has an even number of terms. It skips the step where you have to figure out like what you multiply to, what you add to, our x method of that factoring method, and goes straight to the grouping in pairs. So the first thing you want to check is that there's an even number of terms before you start just grouping in pairs. This one has 4 terms, so that's a good sign. I can just start grouping and taking out the GCF. These two have an x squared in common, leaving over x minus 1. If I group the second two, they have a negative 16 in common, always the sign of the third term, or the first term in your grouping, because now we could have more than 3 terms. And the good thing is, anytime you're dealing with something with matching parentheses, you can factor out the matching parentheses and factor into your matching parentheses times the leftovers. Now I do see an x squared and a minus sign, so I want to check for that difference of squares. I know the square root of 16 is 4, so I want to apply the difference of squares formula here and continue factoring this quadratic. Although you have all of your methods for solving quadratic available to you, you do want to lean on factoring first. So we would factor this into x plus 4 times x minus 4. Use the rest of the equation to finish solving. Set each of those equal to 0, resulting in x equals 1 and plus or minus 4. So we did just use the difference of squares, but here's a reminder of the formula. If you can rewrite something as something squared minus something squared, it factors into a plus b times a minus b, or the square root plus the other square root times the square root minus the other square root. In this unit, we're going to be talking about new factoring rules for the sum of cubes and the difference of cubes. Now notice, for cubes, we have a formula that, yes, you will need to memorize. No, we will not be giving it to you on the quiz. Yes, you would have to use this on a quiz to factor polynomials. The formulas are related. However, there's major difference with signs. The letters are all the same. And it's the same idea that if you can write a 2-term polynomial as a sum of 2 things cubed or a difference of 2 things cubed, you can fill into these formulas. You don't even have to worry about the sign. You're only talking about the number or the variable or the combination of them, because the formula will take care of the signs for you. Now, I just want to point out, there is no sum of squares. We cannot factor a sum of squares. It will not work out. We've already dealt with that issue in these notes up here. Well, kind of. We didn't have a sum of squares because 3 doesn't have a perfect square root, but if you notice, a sum of squares would result in something imaginary. That's why we don't have a sum of squares rule. So our last example is looking at applying one of those formulas. The first thing we want to consider is, how do we rewrite this as a difference of cubes? Well, the cube root of 8 is 2. The cube root of x cubed is x. That becomes our a. The cube root of 27 is 3. Yeah, you do need to know some perfect cubes. So this is A, this is B. We're going to plug into our difference of cubes formula. Here it is. It starts with A minus B times A squared plus AB plus B squared. We're going to plug in our A and our B to that formula, keeping all the signs the same. We don't use the negative with the 3. We only care about the numbers. The signs are taken care of in the formula. So we're going to replace A and B with what they're equal to. We have 2x for every A, and replace all of the B's with 3. To finish factoring this, we would simplify that second set of parentheses by squaring and multiplying everything. Now, be careful here. Remember that the 2 is also squared, so this isn't going to be 2x squared. It's going to be 4x squared. This is the biggest mistake other than, not memorizing the formulas that we see in this section. 2x times 3 is 6x, and 3 squared is 9. Here's our factored form of that difference of cubes. So our first step in this problem is to set it equal to 0 because we are solving by factoring. So we want to work through those guideline steps we looked at earlier in our notes. At this point, I want to see if there's a GCF, and there definitely is because I have x to the fourth and x. So x is definitely part of my GCF. And I'm hopeful that there's a GCF between 54 and 686. So I'm going to take a minute and look for that. It's also even, so I'm going to try 2x as my GCF. I can always see if there's anything else in common after, but I'm pretty confident in 2x. Pulling out the 2x, I end up with 27x to the third minus 343, which makes me happy because 27 and 343 are both perfect cubes, allowing me to rewrite this set of parentheses as something cubed minus something cubed. So I can further factor this polynomial, like I still have the 2x being factored out at the beginning, which will give me a solution to the equation, but I can apply my difference of cubes formula that we just reviewed in the last slide. So we go ahead and factor it as a minus b times a squared, remembering to square both the number and the variable, plus a times b plus b squared. I'm going to pull my GCF down and my equals 0 down to remind myself I am solving this equation. Now here's the thing. Anytime you apply a sum or a difference of cubes formula, the quadratic that results is not factorable. So we have to use our other strategies to solving quadratics to solve that factor of the polynomial. The good thing is we did just cover a unit on solving quadratic functions, so hopefully we remember how to do that. Personally, I'm going to use the quadratic formula. So after I get my quadratic formula and simplifying it, because all of the outside numbers were divisible by 3, I got -7 plus or minus 7i squared roots of 3 over 6 as the solutions to just that one factor. I do need to remember that I should be setting all of my factors equal to 0 to find all of my solutions. So if I set 2x equals to 0, I divide both sides by 2, getting x is equal to 0 as one of my solutions. And 3x minus 7 is equal to 0 gives me x is equal to 7 over 3 as one of my solutions. Altogether, I have 4 solutions again, and I want to list them all in one place. So you do have a couple new formulas to learn, a method that is taken from one of our original methods of factoring, but can be applied to bigger polynomials, and a lot of reminding ourselves how to solve quadratic equations and factor things to solve these polynomials. It's essential that you set the polynomial equal to 0 first and then try to take out any GCFs before you start applying any of your factoring methods.